Hello, I am Sarita, and in this lecture we will be looking at the processes in the interior of stars. We will be beginning with nucleosynthesis beyond the main sequence phase. We have seen in earlier lectures that the main sequence phase involves the fusion of protons to helium nucleus through the pp chains as well as the CNO cycle. Now, is it possible for the nucleosynthesis to proceed beyond the formation of helium nucleus? It is possible provided the conditions are met. That is, at higher temperature and pressure conditions, it is possible for the nucleosynthesis to proceed beyond the production of helium nucleus. So, if the temperatures are high enough of the order of 100 million Kelvin, then the fusion of two helium nuclei gives rise to a beryllium-8 nucleus. But this beryllium-8 nucleus is unstable and can decay back to the two helium nuclei. This is short phase lasts only of the order of 10 power minus 16 seconds. However, during this time interval, if beryllium-8 interacts with another helium-4 nucleus, then it forms a carbon-12 along with the release of energy. Thus, essentially, this set of reactions is a three-body reaction of 3 helium nuclei. Hence, it is known as the triple alpha reaction. The energy generation rate is given by the expression shown here. Here, of course, we have the mass fraction of helium, which is given by Y. And one can see that the energy generation rate is again a complex function of the temperature and the exponential power of temperature. And if one fits a simple power law to this function of energy generation rate close to 100 million Kelvin, then one finds that this goes as the 41st power of temperature. Thus, a small change in temperature leads to a very, very large change in the energy generation rate. Is it possible that nucleosynthesis can proceed further from carbon? Yes, it can. At higher temperatures of the order of 100 to a billion Kelvin, a number of nuclear reactions are possible. For example, the carbon-12 nucleus can interact with an alpha particle to produce oxygen-16 nucleus along with the release of energy, which in turn can interact with an alpha particle to produce neon. Similarly, two carbon nuclei can undergo fusion to produce a range of nuclei such as oxygen, neon, sodium and magnesium, and these happen at successively higher temperatures of the order of 600 million kelvins. And of the order of billion kelvins, we have the nuclear reaction of two oxygen nuclei, giving rise to more products such as magnesium, silicon, phosphorus and sulfur. Thus, the nucleosynthesis proceeds in the production of heavier and heavier nucleus till it reaches iron. This is because we know that from the binding energy curve that the iron nucleus is the most stable nucleus, and fusion is favorable for elements which are lighter than iron. Now, what happens to the iron nucleus when the temperatures go very high as well as the densities go very high? Since the nucleosynthesis does not favor the further nuclear fusion, iron 56 nucleus undergoes photodisintegration to produce helium nuclei or alpha particles. These helium nuclei can further undergo photodisintegration to produce protons and neutrons, and this happens at very high temperatures of the order of 8 to 10 billion kelvins, and this usually occurs in the centers of stars whose mass is greater than 10 solar masses. Thus, we see that although nucleosynthesis had led to the production of various elements, all these reactions are undone at these very high temperatures, and at very high densities which prevailing in the centers of these stars at these temperatures, one finds that the protons and electrons are also squeezed together, leading to the formation of neutrons. Thus, one finds that in the core of very high mass stars in later evolutionary stages, the star is essentially made up of neutrons. Now, let us try to understand how the energy that is generated in the star is transported outside. We again take the case of the sphere, which represents the star, and a shell of mass dm located at a distance r. Thickness of the shell is dr, and we define L of r and L of r plus dr to be the energy per unit time passing through the surface r and r plus dr. Now, the change in luminosity dl between these two surfaces is equal to the energy produced in the shell. That is, dl is equal to epsilon times 4 pi r square rho dr, where rho is the mass density and epsilon represents the energy generation rate per unit mass per unit time. This gives us the relation dl by dr is equal to 4 pi r square f of r, where f of r is defined as a flux which is equal to the mass density times epsilon. F of r is the energy passing through unit area in unit time at the surface r. This equation represents the energy conservation equation, and the energy radiated is generally produced very close to the core, either in the core itself or very close to it in a shell around the core, usually in the interiors of stars. The outer layers hardly participate in this process, and the energy production in the outer layers is negligible. Now, let us look at how the energy that is produced in the layers close to the interior is transferred outside. The transfer of energy usually happens through three processes. One is radiation, the other is convection, and the third is conduction. So, in radiation, energy is transferred through photons. Photons are absorbed by atoms, ions, or nuclei, and they are emitted in random directions, and this transfer leads to the transfer of energy. This scattering and absorption and emission leads to the transfer of energy from the interior to the outside. The second process, convection, involves the physical transfer of hot buoyant mass with excess energy outside, and the cooler parcels of gas from outside fall inwards to replace the hot mass. Thus, there is no net transfer of mass in the convection process. The third process is conduction, which is the transport of heat by collision between particles. It is generally insignificant in most stellar environments. However, in certain regions and in certain stars, this can become important. Let us look at the transfer of radiation through a medium. This is important because for the energy that is coming out from the medium, if we are able to analyze, then we can get an idea of the properties of the medium. For this, let us take the case of a plane parallel medium whose thickness is ds, and the area through which the radiation passes through is given by dA. I nu naught represents the plane parallel rays from a distant source at frequency nu, and I nu is the outcoming intensity from this medium. Then the change in intensity in the medium dI nu is given by the change in energy dE nu per unit area, per unit time, per unit solid angle, and per unit frequency. The medium can be characterized by certain properties, and one of the properties is the emission coefficient. The emission coefficient is given by the change in energy by the medium, or the energy emitted by the medium per unit volume, per unit time, per unit solid angle, and per unit frequency. It can also be written in terms of emissivity, where one writes the change in energy in terms of per unit mass of the medium. Thus, one sees that the change in intensity of the radiation passing through the medium is related to the emission coefficient times the length through which the radiation is passing through. The other property of the medium is absorption, and this is characterized by the absorption coefficient. The absorption of radiation in the medium depends on the intensity of the medium. Therefore, the change in intensity is given by the absorption coefficient multiplied with the intensity, and this absorption coefficient is defined per unit length of the medium. It can, for a homogeneous medium, this absorption coefficient can be written as a product of the absorption cross section and the number density of the particles in the medium. It can also be written in terms of the mass absorption coefficient and the mass density. So, thus we see that the medium can absorb as well as emit radiation when some radiation is incident on this. The outcoming radiation therefore has important signatures of the medium. The change in intensity, outcoming intensity, is given by the emission from the medium minus the absorption due to the medium. Thus, we see di nu is equal to j nu ds minus alpha nu I nu ds, or di nu by ds, that is the change in intensity per unit length, is equal to the emission coefficient minus the absorption coefficient times the intensity. Before we look at the general solution to this equation, which is also known as the radiative transfer equation, we consider two limiting cases. In the first limiting case, we assume that there is no absorption and only the medium is emitting, that is alpha nu equal to 0. Now, the radiative transfer equation reduces to di nu by ds is equal to j nu. This can be solved trivially if one assumes that the medium is homogeneous and therefore the emission coefficient is constant. Thus, from the graph we can see that across the medium the intensity is increasing linearly with length, that is given by j nu. Now, the other limiting case is when there is only absorption and there is no emission by the medium. In this case, the radiative transfer equation reduces to di nu by ds is equal to minus alpha nu I nu, and this can be solved to give I nu is equal to I nu naught times exponential of minus integral of the absorption coefficient along the length of the medium. This integral of the absorption coefficient along the length of the medium is a quantity known as the optical depth. This optical depth is a quantity that tells how much the medium is absorbing the radiation. And if we again consider the case of a homogeneous medium, we see that across the medium, because of absorption, the change in intensity is an exponential drop. We have seen that the medium is characterized by the emission and the absorption coefficients. These two can be combined together in the form of a source function. The source function S nu is defined as the ratio of the emission coefficient to the absorption coefficient, and the radiative transfer equation can now be written in terms of the source function, where all the properties of the medium are included in one term. And the radiative transfer equation therefore can be written in terms of optical depth, that is the change in intensity as a function of optical depth of the medium, and the equation reduces to di nu by d tau nu equal to minus I nu plus the source function. For a simplistic case of a homogeneous medium, the source function is constant, and one can get a general solution to the radiative transfer equation, which is shown here. Very often, for simplicity, one assumes that the source function is equal to the black body a black body function at a temperature T. In the cases considered, we have not considered the case of scattering, because radiation can also be scattered in the medium. We have only considered the cases of absorption and emission. However, scattering can also be included in the radiative transfer equation along with the absorption coefficient term, because the scattering is also dependent on intensity. Therefore, detailed modeling of the radiative transfer equation does incorporate the effects of scattering along with absorption. The optical depth is a very important parameter, as it gives us an idea of the properties of the medium. If the medium is optically thick, that is the optical depth is much larger than 1, then the medium is mostly opaque, that is hardly any radiation is reaching out, that is information about the incident radiation is lost. Therefore, the radiation that is outcoming is the same as the source function. For the other extreme case, when the optical depth is much smaller than 1, we say this is the case of optically thin emission. In this case, there is hardly any absorption and almost all the incident intensity is transmitted out, that is the medium is transparent. In this case, I nu tau is equal to I nu naught. As radiation can also be considered to be photons, using the terminology which has been described, it is possible to estimate the mean free path of the photons in the medium. The mean free path of photon represents the average distance travelled by the photon before it is absorbed. Therefore, in this case, we take the average tau is equal to 1. This can be written as an integral of tau multiplied with the probability of the absorption, which is given by e power minus tau. So, when average value of tau is equal to 1, we can also write tau as the product of the absorption coefficient and the average distance it has travelled before being absorbed, that is L nu. Thus, L nu, which is the mean free path, is given by the inverse of the absorption coefficient. Thus, the absorption coefficient provides us with an idea about the mean free path that the photon travels before it is absorbed. Now, let us look at the radiative transfer in the case of a star. We had looked at the simplistic case of a plane parallel geometry. However, in the case of a star, we look at a spherical geometry. We are interested in the transfer of radiation from the center outwards, that is along the radial direction. However, a photon can take any arbitrary path, which is shown by the direction ds. This has to be transferred along the radial direction, and therefore, the intensity term has a cosine theta factor introduced. Another important consideration in the radiative transfer in the case of a star is an assumption of thermodynamic equilibrium, rather local thermodynamic equilibrium. The star we know is not in a complete thermodynamic equilibrium because the energy is being transferred outside. If it were all at same temperature, there would be no net transfer of heat. However, locally across the mean free path, one sees that the change in temperature is negligible corresponding to the temperature at that location. That is, when the photon is absorbed as well as emitted, the change in temperature is negligible. Therefore, the system can be said to be in a thermodynamic equilibrium locally. This is also known as local thermodynamic equilibrium. And in the case of a star, the source function is taken to be a black body function, and locally this will have a certain temperature T. For the star, across a small region, one can assume that the intensity is almost constant and is given by this approximation shown here. This is known as the Rosseland approximation, where I nu is given by the black body function minus the cosine theta of the radial derivative of the black body function divided by the opacity and the mass density. In order to understand the change in intensity as a function of temperature, one needs to integrate I nu cos theta over all the solid angles and frequency. Now, integration of the opacity as a function of frequency is very involved because there can be many sources of opacity, and these could depend on temperature. It is usually the norm to introduce a frequency averaged opacity, which is also known as the Rosseland mean opacity. After introducing this Rosseland mean opacity in the expression above, when one integrates I nu cos theta, over frequency and the solid angle, we get the derivative of temperature as a function of the flux, the opacity, the mass density and temperature. This equation is known as the equation of radiative transfer in the star, and it gives the temperature gradient due to the transfer of radiation f of r at a distance of r. Thus, dt by dr is equal to minus 3 kappa rho f of r by 64 pi sigma T cube r square. Here sigma is the Stefan-Boltzmann constant. We see that opacity is an important factor in the temperature gradient of a star. There are various physical processes which contribute to the opacity in stellar interior, and here we briefly list them. In ionized gases, electrons are an important source of opacity. These electrons could scatter radiation or they could also absorb radiation. When the radiation is scattered, that is the incoming radiation is just scattered in different directions. This is known as opacity due to electron scattering. Electrons can also absorb in the vicinity of ions, and this is known as free absorption. In regions with relatively lower temperatures, that is less than a million Kelvin, there are other sources of opacity that come into picture. These are bound-free and bound-bound absorption. These represent the absorption of photons due to ionization of atoms or ions, or the transitions between energy levels in atoms or ions. And this absorption of photons is known as the bound-free opacity due to ionization, or bound-bound opacity due to the absorption of photons leading to the change in energy levels of the atoms. In even cooler stars where the temperature is less than 3 to 6000 Kelvin, negative hydrogen ions are an very important source of opacity. Negative hydrogen ions are formed when the neutral hydrogen atoms are bound by free moving electrons. The ionization potential of these negative hydrogen ions is very small, and therefore of the order of 0.7 eV, and therefore they can easily absorb photons. Thus, to dissociate and form an electron and a hydrogen atom. Thus, at these temperatures, negative hydrogen ions are an important source of opacity. At even lower temperatures, when the effective temperatures are less than 4000 Kelvin, that is in very cool stars, molecules and dust could be present. These can also absorb radiation. Thus, we see that the absorption of radiation leading to various scattering processes or absorption processes leads to an increase in opacity. Next, we look at the other mode of energy transfer in stars. Due to opacity and other factors, radiative transfer in a star can be inefficient. As a result, the temperature gradient increases. If we want to understand convection, then it is important to understand how the temperature gradient affects the convection process. The convection process is usually very effective when energy cannot be transferred by radiation. Therefore, to derive a condition for energy transfer by convection, we consider the condition of adiabaticity. That means energy is unable to get transferred outside. The condition of adiabaticity is PV power gamma is equal to constant, where gamma is the adiabatic index and is given by the ratio of specific heat at constant pressure to the specific heat at constant volume. When this equation is applied to the ideal gas equation, then we get that the temperature is proportional to P power 1 minus 1 by gamma. Taking a derivative of this equation, we find that dt by dr is equal to 1 minus 1 by gamma times T by P times dP by dr. and this is this temperature gradient is the adiabatic temperature gradient. When the temperature gradient in the star approaches the adiabatic temperature gradient or exceeds the adiabatic temperature, then a convection begins to take place. The convection, as mentioned earlier, the convection actually just moves the hotter gas outside, and the cooler gas from outside falls inside with no net transfer of mass. As a result, in the convective region, the gas is homogeneously mixed, and this is found to be important in those cases where most of the star is convective, and the inner nuclear processed elements could be transferred outside to the surface as a result of this convection. Thus, in summary, for a star in equilibrium, there are 4 equations that describe the stellar structure. They are the following, which have already been discussed. One is the pressure gradient, which is the hydrostatic equilibrium condition. dP by dr is equal to minus gm rho by r square. Then we have the mass continuity equation. dm by dr is equal to 4 pi r square rho. We have the energy conservation equation. dl by dr is equal to 4 pi r square f of r. And finally, the temperature gradient due to the radiative energy transfer, which is given by dt by dr is equal to minus 3 kappa rho f of r by 64 pi sigma t cube r square. We see that the hydrostatic equilibrium condition as well as the radiative transfer condition are negative. This implies that the pressure gradient as well as the temperature gradient are negative. Since the radial direction is considered outward from the center to the surface, this means that the temperature and pressure are highest at the center and falls off as we move towards the surface. Is there some way to look at the temperature gradient from the picture of a star? Yes, this is possible. Let us consider the case of the picture of the sun. Here, from this picture, one can see that the intensity is maximum at the center, and towards the edges, we see that the intensity has dropped. This effect is known as limb darkening effect. How do we understand this? This can be understood as a combination of energy generation at the center as well as geometric effects of the optical depth. When we are looking at the center of the star, we are able to probe deeper, higher temperature layers as compared to when we are looking at the edges. At the edges, we are looking inward only towards the lower temperature layers. This also helped to define what is known as the photosphere. The photosphere is the region from which the photons that we see originate, and this is taken to be the optical depth from the observer towards the star as tau is equal to 2 by 3. Thus, the photosphere is defined as the region where tau is equal to 2 by 3, and this the photospheric layer could therefore be different at different frequencies because optical depth is frequency dependent. With this, we come to the end of this lecture. Thank you.